What if everything we think we know about the Big Bang is incomplete? What if that cosmic explosion that created our universe didn't just create one reality, but two? Today, we're diving deep into one of the most mind-bending theories in modern cosmology. The idea that the Big Bang created a mirror universe that expands in the opposite direction through time. This isn't science fiction, this is cutting-edge theoretical physics proposed by some of the world's leading cosmologists, including Neil Turok from the University of Edinburgh and Latham Boyle. Their CPT symmetric universe theory doesn't just challenge our understanding of the Big Bang, it potentially solves some of the biggest mysteries in cosmology.
How did everything we see come out of a single point? That's what the Einstein equations imply, and it's very mysterious indeed. Hawking's picture was very geometrical. He said, let's trace the Big Bang back to the singularity. Space is shrinking to a very small point. We can sort of think of this like a cone whose tip is sharp. And so, if you like, the cross-sections of the cone, as you go up the cone, that's time, and the cross-sections denote space. And so the cross-sections are a circle, which is shrinking to a point at the Big Bang.
But before we explore this revolutionary idea, we need to understand what we're trying to fix about our current model of the universe. The problems with our current understanding. Our current understanding of the universe's origin relies heavily on two major theoretical frameworks: cosmic inflation and string theory. According to the Standard Model, the universe began as an infinitely dense point called a singularity, then underwent a period of rapid expansion called inflation, stretching from smaller than an atom to larger than a grapefruit in a fraction of a second. But here's the problem. The more we observe the universe with our most powerful telescopes, the simpler it appears to be. As Neil Turok points out in his recent work, we live in a golden age for learning about the universe. Our most powerful telescopes have revealed that the cosmos is surprisingly simple on the largest visible scales. 1. Meanwhile, our theoretical models predict incredible complexity. The string theory dilemma, string theory, often called the theory of everything, suggests that the fundamental building blocks of reality are tiny vibrating strings. But there's a catch. The theory only works if there are more dimensions of space than the three we experience. String theorists assume these extra dimensions are curled up so small we can't detect them. This creates what physicists call the landscape problem. There are an almost unimaginable number of ways these extra dimensions could be arranged. Potentially 10 circumflex, 500 different configurations, each giving rise to completely different physical laws. Despite decades of research and billions of dollars in funding, string theory has yet to make a single successful prediction about the real world, the inflation paradox. Cosmic inflation was proposed in the 1980s to explain why the universe appears so smooth and flat on large scales. The theory suggests that a brief burst of exponential expansion smoothed out any initial irregularities and flattened the geometry of space. But inflation makes a crucial prediction. It should have generated long wavelength gravitational waves, ripples in space-time itself. These waves would be a smoking gun proving inflation actually happened. The problem? Despite increasingly sensitive experiments, we haven't detected any such waves. In fact, as our instruments have improved, more and more models of inflation have been ruled out. 2. Even worse, inflation naturally leads to what's called the multiverse, an infinite collection of universes with completely different physical properties. This makes the theory fundamentally unpredictable and untestable, violating basic principles of scientific methodology. But perhaps the biggest problem with our current understanding involves one of the most fundamental questions in cosmology. Why does anything exist at all? According to the Standard Model of particle physics, the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other completely, releasing pure energy. If the universe started with equal amounts of both, everything should have been destroyed, leaving behind only photons in an empty cosmos. Yet here we are. Somehow there was a tiny excess of matter over antimatter, about one extra matter particle for every billion matter-antimatter pairs. This asymmetry is what allowed stars, galaxies, planets, and ultimately life to exist. But the mystery deepens when we consider dark matter. This invisible substance makes up about 85% of all matter in the universe, yet we have no idea what it is. It doesn't interact with light or ordinary matter except through gravity, making it incredibly difficult to detect directly. Enter CPT symmetry. To understand the revolutionary solution proposed by Turok and his colleagues, we need to grasp one of the most fundamental principles in physics, CPT symmetry. CPT stands for three basic transformations. C, charge, replace every particle with its antiparticle P, parity. Look at the mirror image of a process T, time. Run the process backward in time. The CPT theorem states that any physical process should look identical if you apply all three transformations simultaneously. This isn't just a mathematical curiosity, it's one of the most fundamental symmetries in nature, deeply connected to the structure of space-time itself. But here's the problem. Our universe appears to violate CPT symmetry. Time always moves forward, and we have more matter than antimatter. According to CPT symmetry, this shouldn't be possible in a complete physical system. The mirror universe solution. This is where the mirror universe theory comes in. What if the universe doesn't actually violate CPT symmetry? What if we're only seeing half the picture? In 2018, Latham Boyle, Kieran Finn, and Neil Turok published a groundbreaking paper proposing that the state of the universe does not spontaneously violate CPT. Instead, the universe after the Big Bang is the CPT image of the universe before it, both classically and quantum mechanically. 3. Picture the Big Bang not as an explosion from a point, but as a mirror in time. On one side, our side, time flows forward and matter dominates. On the other side, time flows backward and antimatter dominates. Together, these two universes form a complete CPT symmetric system, the technical foundation. The mathematical foundation for this idea comes from something called conformal symmetry. This deep symmetry in the laws governing light and massless particles means that neither light nor massless particles actually experience the shrinking of space at the Big Bang singularity. By exploiting this symmetry, Boyle and Turok found they could follow light and particles all the way back through the Big Bang and into a pre-Big Bang era. What they discovered was remarkable. The initial singularity could be described not as an infinitely dense point, but as a mirror, a reflecting boundary in time. As Turok explains, when you look in a mirror, you see your mirror image behind it. If you're left-handed, the image is right-handed, and vice versa. The combination of you and your mirror image are more symmetrical than you are alone. 4. One of the most elegant aspects of the mirror universe theory is how it naturally explains dark matter without requiring any new particles beyond those already in the standard model. The key lies in neutrinos, those ghostly particles that barely interact with ordinary matter. We know of three types of neutrinos: electron, muon, and tau neutrinos. But these are all left-handed, meaning they spin in a particular direction relative to their motion. Most other particles come in both left-handed and right-handed versions, so physicists have long suspected that right-handed neutrinos should exist. The problem is that right-handed neutrinos would be incredibly difficult to detect. They would interact only through gravity, making them essentially invisible. In the CPT symmetric universe model, these right-handed neutrinos are naturally produced in abundance. Boyle, Finn and Turok calculated that to match the observed dark matter density, one of these right-handed neutrinos would need to have a mass of approximately 4.8 x 10 circumflex 8 GeV, about 500 million times heavier than a proton. This makes right-handed neutrinos perfect dark matter candidates. They're stable, they don't interact with light or ordinary matter except through gravity, and they arise naturally from the mirror universe model without requiring any exotic new physics. Before we go further, let's address some common misconceptions about the mirror universe theory. Misconception 1. We could travel to the mirror universe. Reality. The mirror universe exists behind our Big Bang, before the beginning of our cosmos. It's not a place you could visit. It's more like a mathematical reflection that ensures the overall system obeys CPT symmetry. Misconception 2. This is the same as parallel universe theories. Reality. Unlike science fiction parallel universes, the mirror universe is specifically the CPT reflection of our universe. It's not an alternate reality with different histories. It's the necessary complement that makes the total system symmetric. Misconception 3. This violates causality. Reality. The mirror universe doesn't violate causality because we can never interact with it. The Big Bang acts as an absolute boundary. Information cannot pass between the two sides. One of the most profound implications of the mirror universe theory involves the arrow of time itself. Why does time seem to flow in only one direction? Why do we remember the past but not the future? The answer lies in entropy, the measure of disorder in a system. In our universe, entropy increases as time moves forward, but in the mirror universe, entropy also increases as time moves forward from its perspective, which means it decreases as we look backward from the Big Bang. Turok and Boyle extended Stephen Hawking's work on black hole entropy to calculate the gravitational entropy of the entire cosmos. They found that entropy is maximized for flat, uniform universes, exactly what we observe. This provides a natural explanation for why the universe appears flat without requiring inflation.
So basically he was saying that the natural arrow of time, somebody would conclude if they observed such a thing, is that time is going backwards when everything is sort of assembling into this corner, but time is going forwards when everything comes out of the corner. So Boltzmann tried to sort of assume that the universe we see began in a very rare event. And that very rare event was sort of created by things going backwards in time to create it. And I think that's a very beautiful idea.
Unlike string theory and many inflation models, the CPT symmetric universe theory makes specific testable predictions. Prediction 1, no primordial gravitational waves. Since the theory doesn't require inflation, it predicts no long wavelength gravitational waves from the early universe. Current observations are consistent with this prediction, as no such waves have been detected despite increasingly sensitive experiments. Prediction 2, neutrino properties. The theory predicts that the 3 light neutrinos are Majorana particles, meaning they are their own antiparticles, and that the lightest neutrino is exactly massless. These predictions can be tested with neutrinoless double beta decay experiments and precision neutrino mass measurements. Prediction 3, dark matter mass. The theory gives a specific prediction for the dark matter particle mass, 4.8 x 10 circumflex 8 GeV. While this is far too heavy to produce in current particle accelerators, future astronomical observations might be able to detect signatures of such massive particles. The mirror universe theory also addresses another major puzzle in physics, the strong CP problem. This involves a parameter in quantum chromodynamics, the theory of the strong nuclear force, that should cause neutrons to have an electric dipole moment. Experiments show this moment is incredibly small, much smaller than theory predicts. In a 2022 paper, Boyle, Tuscher, and Turok showed how the Big Bang as a mirror provides a natural solution to this problem. By treating the standard model as the limit of a minimal left-right symmetric theory, they obtained a cosmological solution that eliminates the strong CP problem without requiring additional particles like axions. Like any revolutionary scientific theory, the CPT symmetric universe model faces challenges and criticisms from the scientific community. Critics argue that the theory still requires passing through a singularity at the Big Bang, where the laws of physics break down. While the conformal symmetry approach provides a mathematical framework for handling this, some physicists remain skeptical about whether it truly resolves the singularity problem. The theory relies on classical general relativity and quantum field theory, but near the Big Bang, quantum gravity effects should become important. A complete theory would need to incorporate quantum gravity, which we don't yet fully understand. While the theory makes testable predictions, many of them are at the edge of current observational capabilities. Detecting the predicted neutrino properties or ruling out primordial gravitational waves requires extremely sensitive experiments that are still being developed. The field has seen significant developments since the original 2018 paper. In 2022, the same team published additional work on how the mirror universe solves the strong CP problem. More recently, other researchers have explored extensions and implications of the theory. Several upcoming astronomical surveys, including the Euclid satellite mission and the Vera Rubin Observatory, will provide new tests of the theory. These observations will measure the properties of dark matter and the expansion history of the universe with unprecedented precision. If the CPT symmetric universe theory is correct, it would revolutionize our understanding of cosmology in several ways. The theory suggests that the universe is fundamentally simple rather than complex. This goes against the current trend in theoretical physics toward increasingly elaborate models with many free parameters. The theory provides an alternative to cosmic inflation that explains the observed properties of the universe without requiring a period of exponential expansion. This could fundamentally change how we think about the early universe. By identifying dark matter with right-handed neutrinos, the theory solves one of the biggest mysteries in cosmology using only particles that should already exist according to the standard model. Beyond the technical details, the mirror universe theory raises profound philosophical questions about the nature of time, causality, and existence itself. If time flows backward in the mirror universe, what does this mean for our understanding of causality and free will? The theory suggests that the arrow of time emerges from the statistical behavior of matter and energy, rather than being a fundamental property of space-time. Unlike multiverse theories that postulate infinite universes with random properties, the mirror universe theory suggests our universe has a unique necessary complement. This restores a sense of cosmic purpose and inevitability that many find philosophically appealing. The next decade will be crucial for testing the CPT symmetric universe theory. Several key experiments and observations will provide definitive tests. Advanced gravitational wave detectors will search for primordial gravitational waves with unprecedented sensitivity. The absence of such waves would support the mirror universe theory over inflation. Next-generation neutrino experiments will measure neutrino masses and search for neutrinoless double beta decay. These measurements will test the theory's predictions about neutrino properties. While the predicted dark matter particles are too heavy to produce in accelerators, astronomical observations might reveal their signatures through gravitational effects or rare interactions. The CPT symmetric universe theory represents a bold attempt to solve some of the deepest mysteries in cosmology with elegant simplicity. By proposing that the Big Bang created not one universe but two mirror images of each other expanding in opposite directions through time, the theory potentially explains dark matter, the matter-antimatter asymmetry, and the arrow of time itself. Whether this theory will ultimately prove correct remains to be seen. Science progresses through bold hypotheses that make testable predictions, and the mirror universe theory certainly fits this description. As Neil Turok emphasizes, time will tell whether they survive further scrutiny. However, the progress we have already made convinces me that, in all likelihood, there are alternatives to the standard orthodoxy. What makes this theory particularly compelling is its commitment to simplicity and testability. Rather than adding new particles or dimensions, it works with the physics we already know, making specific predictions that can be verified or falsified by observation. As we continue to probe the deepest mysteries of existence, theories like the CPT symmetric universe remind us that the most profound truths about reality might be simpler and more elegant than we ever imagined. The universe may indeed be stranger than we suppose, but perhaps it's also more beautiful. What do you think about the mirror universe theory? Does it solve the problems of cosmology, or does it create new ones? Let me know in the comments below, and don't forget to subscribe for more deep dives into the mysteries of the cosmos.